So we're considering the topic electrolysis. Electrolysis. Now, what is electrolysis? Electrolysis is the process of decomposing or breaking down certain solutions or liquids or melted substances into their component parts by passing electricity through them. The process of breaking down certain solutions. Solutions can be liquids, or they are molten substances. Molten means melted. When you break those substances down into their component parts, let's say we have a compound HCl, hydrochloric acid. We want to break them into their component part, means we want to break them apart into hydrogen and chlorine. So substances can be broken down into their different component parts by passing electricity through them. And of course, you know that when substances are in solid forms, they cannot conduct electricity. So because their ions are locked, they are in solid form, their ions are static, they are not movable. So that's why it cannot conduct electricity. So these substances have to be dissolved in water. They have to be melted. That's why we call it molten. They have to be dissolved in water. And when they are dissolved in water, the force of attraction that held them together in the solid form, they are broken. And you break these bonds apart, then the ions are free to move. Now, when these ions are free to move, then you can say that substance can be able to conduct electricity. Now, it's such substances where the electrons or the ions are free to move that we use in electrolysis, because we want to pass electricity through them. Now, these substances which are in liquid form, molten form, and can conduct electricity, in electrolysis, these substances are known as electrolytes. Electrolytes. Therefore, an electrolyte is a molten or melted compound that conducts electricity. Now, it is this electrolyte, it is this melted substance which can conduct electricity that is our raw material now. That is the substance we want to break down into their different ions. Since the ions are free to move, okay, we can separate their ions. Let the positive ions go one way and let the negative go the other way. So we want to break down this molten substance, this electrolyte, into the different component parts. So in electrolysis, we're not going to just be saying break down. We'll be calling it decomposition, or we call it dissociation. So we want to dissociate the ions, we want to decompose the ions. You understand? So now, it is this electrolyte that is being decomposed, you understand, into their ions. Now, there are two types of ions. You already know this. We have anion and cation. Now, you can call the anion the anode's ion. That is, the ion that will go to the anode. You understand what anode is very soon. And you can call cation the cathode's ion. That's the ion that will migrate to the cathode. Now, in a brief way, anode is the positive electrode. You will still discuss what electrode is. So anode is the positive electrode, while cathode is the negative electrode. Now, but cation is the positive ion and anion is the negative ion. So the positive ion, cation, will have to move to a negative electrode, which is the cathode. So that's why I'm saying you call cation the cathode's ion, the ion that will move to the cathode. While anion, which is a negative ion, will have to move to a positive cathode. So you call anion anode's ion. I hope you understand. Okay. Now, non-electrolytes are solutions of organic substances which produce molecules instead of ions. We know for substances to conduct electricity, they have to consist of ions. So if we say that, then other substances which can be in liquid form, we say when they're in liquid form, they are free, the ions are free to move, and so they can conduct electricity. Now, some other liquids, some other molten forms of compounds that don't have ions cannot conduct electricity because they don't have ions. Now, these kind of substances are called non-electrolytes. They are not electrolytes. Whereas electrolytes can conduct electricity, non-electrolytes will not be able to conduct electricity. So non-electrolytes produces molecules instead of ions. So there are 4 conductors of electricity. So non-electrolytes include sugar, ethanol, glycerin. You have urea, your urine, part of your urine. You have starch and acetone and many others. Those are non-electrolytes that cannot conduct electricity. Take note. Okay. Now remember I said the anion is the anode's ion and the cation is the cathode's ion. Now, what are these? What is cathode? What is anode? So, electrodes are conductors in form of wires, rods, or plates through which electric current enters or leaves the electrolytes. So electrodes are conductors. Conductors are materials or substances that can allow electric currents to pass through them. So number one, an electrode must allow electric currents to pass through it. So electrodes are conductors, and they can come in different forms. Some electrodes that come in wire forms. They can be like wires, like you have your normal electric wires. They can be like in form of rods, and they can also be in form of plates. But what is paramount is that the electrodes have to conduct electricity. It has to allow electric current to pass through them. Now, it is through this electrode that electric current will enter into the electrolyte. Remember, electrolyte is that substance that is in molten form now, which we want to decompose into their different ions. So it's the electrode that will bring in the electric current into that electrolyte. So one electrode will bring in the current. The current will leave at the other end, the other electrode. So the current enters the electrolyte through one electrode and leaves the electrolyte through the other electrode. Remember, flow of electron continues. So it enters, leaves, enters, leaves. All right. Now in electrolysis, there are two electrodes. Now, remember we said they must conduct electricity. Now, what are these two electrodes? We have the negative electrode, and it's called cathode. The negative electrode is called cathode, and it's attached to the negative terminal of the power pack. If you look at your cables, your wires, you see two wires inside, black and red. The red one is the negative, so the black one is the positive. So that red one should be connected to your cathode to make that cathode the negative electrode. Good. Now I want you to think of a cathode as it is being covered with electrons. It has so many electrons. Now, if it has so many electrons, then it will be giving electrons to ions. So it will be attracting positive ions so that it can give electrons, because electrons are negative. It will be attracting positive things so that it can give them the negative thing and become neutral itself. You understand? But it has so many, so it can give so many to whichever ion needs them. Now the positive electrode is the anode. Remember, the negative electrode is the cathode, so the positive electrode is the anode. And since the cathode is covered with electrons, think of the anode as being lacking electrodes, doesn't have electrodes, since it's the opposite of cathode. The anode does not have electrons, so it lacks electron, it needs electron. So it lacks electron. But the cathode has a lot of electrons. So if this happens, this means that if you insert these two electrodes into an electrolyte, electrolyte must have ions, positive and negative. It means the anode, which has no electrode, will be extracting the electrons. The cathode, the anode, which has no electrons, will be extracting the electrons from that electrolyte to itself. So the electrons which are negative in the electrolyte, remember electrolyte is this liquid substance that was that we want to dissociate into their different ions. So since the anode has no electrons, it's looking for electrons, it doesn't have any, and you put in a substance that has positive and negative ions, and the negative are electrons. Wow, the anode sees that, oh, there are electrons in this liquid that I'm seeing. It will attract those ones that it needs since it doesn't have them. So that's why the anode attracts negative ions. Whereas since the cathode has already electrons which are negative, it will be looking for positive ions, to be looking for cations, and it will be collecting the cations from the electrolytes. So if the anode is busy collecting the electrons from the electrolytes, which are the negative ions, and the cathode is busy collecting the cations, which are the positive ions, from the electrolyte, at one point all the cations, all the positive ions will move to the cathode, and all the negative ions will move to the anode, and you will discover that the ions in the electrolyte has been completely dissociated, divided into two, so the electrolyte becomes free and you have your ions separated. That's the essence of electrolysis. So take note, reduction takes place at the cathode. Remember, what is reduction? Reduction is gain of electrons. So remember, the positive ions in the electrolyte will go to the cathode. Since the cathode has so many electrons, what will it be doing? It will be collecting the electrons. What is it doing? It is gaining electrons. So when you gain an electron, that's reduction. So reduction takes place at the cathode, while oxidation takes place at the anode. So the negative electrons, the negative ions in the electrolyte will be running to the anode. The anode does not have electrons. So when the negative ions in the electrolyte go to the anode, they'll be giving that their electrons to the anode and become more positive. So what are they doing? They are losing electrons. They are losing their electrons. So oxidation is loss of electrons. So oxidation takes place at the anode. Take notes of that explanation. Reduction takes place at the cathode because the positive ions in the electrolyte will move to the cathode, and we said think of cathode as being covered with electrons. It has so many electrons. The positive ion, when it goes there, will collect that. Remember, when it collects, it will collect the electrons, to gain the electron from that cathode and become neutral. So if it was 5 positive ions inside, it will go and gain 5 negative electrons and become neutral. So, but what it's doing is it's gaining electrons, right? Because it is positive, it has to gain negative thing to become neutral, remember. So it's gaining electron, and gain of electron is reduction. So therefore means reduction takes place at the cathode. And the other way around, the negative ions, which are the electrons, move to the anode. Since the anode does not have electron, it's positive. So negative stuff will move to positive electrode and lose its negative things so that it can become neutral. Remember we said elements or substances can either gain electrons to become neutral or they lose electrons to become neutral. So these negative ions will go to the positive electrode, which is the anode. They will lose their negative stuff, they will lose their electrons. So what are they doing? Loss of electrons, which is oxidation. So therefore means oxidation takes place at the anode. Okay, so remember I gave you a little trick the other day on how to know. We used oil rig, oil being oxidation is loss, rig, RIG, being reduction is gain. Now this one you are going to use another trick, another trick to know how to know the difference between where reduction takes place and where oxidation takes place. So we use the words care anox, care, C-A-R-E, anox, A-N-O-X. C-A for care means cathode, C-A, and R-E that completes the care is reduction. So you'll be saying cathode reduction, that's care. So it means reduction takes place at the cathode. Then on the other side, anox, A-N-O-X. The A-N is for anode and the OX is for oxidation. So it will be anode oxidation. So it means oxidation takes place at the anode. So two tricks now, oil rig and care anox. Alright, let's take an example. In the electrolysis of molten lead bromide. Molten lead bromide. You see, molten lead bromide has two ions. It has the positive lead ions, Pb2+, and the negative bromine or bromide ions, 2Br-. Now, since we know that the positive ions will move to the negative cathode, which is called the negative electrode, which is called cathode, then the positive lead ions will be attracted to this electrode, this negative electrode. Remember, opposite charges attract, so positive will be attracted to negative. So since the positive ion to be attracted to the negative electrode, which the negative electrode is the cathode. Now when it goes there, it will deposit, it will gain two electrons. Remember, it has two cations, it has two positive charges, so it will gain two negative charges, right, to become neutral. So it will gain two electrons to become lead atom. Remember I said when it's neutral, no charge on it, you now call it atom, but when it has a charge you call it ion. So to be deposited, it will gain two electrons and become lead atom, Pb. Now, when that happens, a reduction has taken place. So you can write your reduction half equation using that. So, but the bromine ions are negative. So where would they move to? Remember, opposite charges attract. Since bromide ions are negative, it will move to positive electrode, which is what? The anode. So when it moves to the anode, how many electrons will it? How many electrons will it lose? Its bromine has one electron because bromine has one Br, 1-. Good. But when it does, so it will lose that one electron and become neutral. So it will form bromine atom. But remember we said that most halogens are diatomic. It should be written Br2. So because of that, bromine has to react with another bromine and become Br2. So because of that, remember the other day I said we have to put that 2 in the equation to show that bromine actually is diatomic. So that's why the equation has 2 letter 2Br minus, loses 2 electrons and was deposited as bromine atom. Now that's oxidation, so you can use that to write your oxidation equation. Now you've already known this, so let's not waste time there. Okay, now we've defined what electrodes are. We say we have 2 electrodes, the positive electrode, which is the anode, and the negative electrode, which is the cathode. And we say reduction takes place at the cathode and oxidation takes place at the anode. Now let's define another term: electrolytic cell. Electrolytic cell. This is the assembly of 2 electrodes, positive electrode and the negative electrode, in an electrolyte. Remember, the electrolyte is that melted substance that has ions in them and is used for the electrolysis of a substance. So when we say the 2 electrodes, the positive and negative electrodes are dipped into the electrolyte. Now, when they are dipped into electrolyte, they are connected to something, the power source. So these 2 electrodes, when dipped into the electrolyte, the other parts, which is connected to the negative wire and the positive wire, they are all connected. They are connected to a battery, a cell. That's why it's called electrolytic cell. So that when you put on the cell, then electrolysis begins. So the assembly of all these electrodes and everything is fixed and ready for electrolysis. That whole circuit is called electrolytic cell. So electrolytic cell is used to carry out electrolysis process. Now, speaking of process, let's see what these processes are. So we'll be discussing ionic theory. Ionic theory. Now remember the man Arrhenius, when we're discussing concepts of acid, base, and salts, how some people define acid and bases. Remember how Arrhenius defined this acid and base? Well, Arrhenius also postulated a theory for the ionic theory. So his ionic theory states that certain substances produce freely moving ions when they dissolve in water, and these ions, they conduct electricity when they are in solution, when they are dissolved. Good. Now, when electrolytes dissolve in water, they produce ions, but to varying extents. They don't produce these ions in the same way. Some can dissociate their ions into the water easily, and all of the ions, but others may not be able to dissociate all of its ions. So strong electrolytes is the electrolyte that dissociates or dissolve completely into ions. So if you put a strong electrolyte into water, it will dissolve all of its ion into the water, while the opposite, the weak electrolyte, will not dissolve all of its ions into the water. It will just dissolve a small amount, small percentage. Now, what are the key points in this Arrhenius ionic theory? Number 1, the process of splitting of compounds into ions is called ionization. By the time you put your electrolytes in water, and you know the electrolytes must conduct electricity, and it possesses ions, has ions. Now that process where the positive ions will go to the negative electrode, which is the cathode, and they are reduced, and the negative ions go to positive electrode, the anode, and they are oxidized. That process of splitting those two ions, those two types of ions, is called ionization. Number 2, the fraction of the total number of molecules present in solution to the total number of molecules, to the total number of ions, is known as degree of ionization or degree of dissociation. So the total number of molecules present in that water compared with the total number of ions, that means how much the electrolyte dissolved into ions is called degree of ionization. How much of the ionization, how much ionized ions, how much ions we have in the water, the degree of ionization. So the fraction of the total number of molecules present, the molecules that are still present that have not been dissolved into ions, compared to that the fraction of the ions that has been, the part that has been ionized, is called degree of ionization. So I call it degree of ionization or degree of dissociation. All means the same thing: the extent of ionization, the extent of dissociation. Okay, number 3, the splitting of a substance into positively and negatively charged ions in an aqueous solution is called dissociation. Remember, we said that the process of splitting this compound into ions is called ionization. Now, the splitting of a substance into positively and negatively charged ions in water, in aqueous solution inside water, is called dissociation. So don't confuse that with ionization. Ionization is splitting the compounds into ions. The compound has been dissolved into ions. We know these ions are negative and positive now, but their ions are still there inside, all of them mixed. But this process of dividing them, positive go to the other one, negative go to the other one, is called dissociation. Please don't confuse it with ionization. Number 4, ions present in solution constantly reunite to form neutral molecules. The ions present in solution constantly reunite to form neutral molecules. Thus, there is a state of dynamic equilibrium between the ionized and non-ionized molecules. You can see the formula there: AB ionized and produced A and B minus. See, B minus and A can meet again and form AB. You understand? And then it continues that way. So there is a sort of a dynamic equilibrium, equal reactions. Now you can see a formula where we can use to explain that kind of equilibrium. A plus all over AB equals a constant, and this constant is called the ionization constant. Okay, so those are the main points in Arrhenius ionic theory. Now, listen. When these electrolytes are dissolved in water, and the ions have been the ionization has taken place. Remember, splitting into ions, and then dissociation wants to take place. Separating into positive and negative wants to take place. Now, how much or these ions, if they are take for instance, we have hydrogen inside the electrolytes we are dissolving into water, and you discover that water also has hydrogen. Good. Now you want to dissociate the electrolyte which has hydrogen, but the water also has hydrogen. So in the electrodes during electrolysis, water also always want to be fighting also to dissociate its own ions and be deposited as neutral. So now, which one is preferred against the other? Preferred to the other? Will the electrolytic process ionize both of them at once? The water inside the water used in dissolving the electrolyte and the electrolyte itself at once? No, there is a preferential discharge of ions. The electrode will prefer to discharge or to dissociate a particular set of ions before the other. That's what we call preferential discharge of ions. Now listen. During the electrolysis of a given electrolyte, the products formed at the electrodes depend on the nature of the electrolytes. So, nature of the electrolytes. If the electrolyte is a solution, we're explaining the nature now, the electrolytic products formed at the electrodes may vary because the solvent, that's the water, will also ionize. Remember what I said. The water also has ions in them. They want to also attain this ionization state. So in such case, the cations and the anions of both the electrolytes and the water, the solvent, they will all move to the cathode and the anode respectively. If it's the cation, it will move to the cathode, and the anions will move to the anode. But this cation, both the cations of the electrolyte and the cations of the water itself, they will all move. They want to be ionized. Now when they move to these electrodes, they will have to compete with one another to be discharged. So now when this competition starts, the electrode has to choose. The electrode has to decide. Now so the product which is formed at an electrode will depend on which ions are preferentially discharged. Which one does the electrode prefer to discharge first? Do you understand? Okay, so it has to be, is it the ions from the electrolytes or the ions from the water, which is the solvent? The electrode will decide. Now, the discharge of ions is governed by three conditions. Now, let's see how the electrode decides. Number one, the position of the ions in the electrochemical series. The position of ions in the electrochemical series. Now, if you look down, I stepped down and said I explained number one. You will see the relative position of ions in the electrochemical series, and you see that side of cation and the anion differently. On the cation side, you remember the cation will move to the cathode. So if in that electrolyte, any of these cations listed here are there, you will understand how the position in the this electrochemical series you saw there with an arrow going down. You see how the position of these ions in this series can affect how they are preferentially discharged. So we have K at the top, Na second, Ca third, Mg fourth, down till we have Au, which is gold, down there as the cations that will migrate to the cathode. Now the anion side, we have fluorine F there and SO4 2 minus second, NO3 minus Cl, Bri, and OH down here. That's not all, but we can stop there. Now take note of this. You know these ions, the anions will migrate to the anode. So in the electrolytes and the solvents, the anions in both the electrolytes and the solvents will move to the anode. So they will be having one or two of these anions listed here, and the cations in both electrolytes and the solvents will move to the cathode, and they will have one of these cations listed. And when they reach their electrodes, take note of what will happen. The cation that has a lower position in the series are preferentially discharged. So at the cathode, that is the negative electrode, the cathode will decide by selecting the cation that in the electrochemical series it is below the other. So the one that has a lower position in the electrochemical series. So if we look at this electrochemical series, if the cation in the electrolytes had sodium, Na, you can see sodium is second in the electrochemical series, and the cation in the water was had Pb, lead. Okay, let's say it has hydrogen, because water always will have hydrogen. If you look down that cation table, you see hydrogen is further down. In fact, after Na, you have to pass 1, 2, 3, 4, 5, 6, 7, and then hydrogen comes 8 below sodium. So, since the cation with a lower position in the series should be discharged first, then the hydrogen ion from the water will be discharged first. So the electrode has decided, the cathode has decided, okay, since hydrogen is lower in the series, that's the one I will discharge first. So sodium has to wait. Good. Now on the anion side, the anion with a higher position in the electrochemical series are discharged first, preferentially discharged. So if the anion in the electrolytes had fluorine, that's the one at the top there, F, and that in the water had hydroxide here, OH minus, down there. So which one? The anode will say, okay, our own part is that since you are 2, I will discharge first the one that is higher in the series. So fluorine has to be discharged first. So the anion of the electrolyte is discharged first, but the cation or the cation in the water, the solvent, is discharged first on the other side. So the electrode decides which one is discharged first. Now, number 2, we say the concentration of the ions in the electrolytes. The first condition is that the position of the ions in the electrochemical series can affect which one is discharged first or not. Now, the second one is that the concentration, how much ions in the electrolytes, that's the concentration, can also decide which one is discharged first. Now, increasing the concentration, that's the amount of ions, of a given ion tends to promote its discharge from solution. So the ion that has more concentration can be dissolved more preferentially. The influence of concentration, however, is effective only when the two competing ions are closely positioned in the electrochemical series. Condition number 2 will not disregard condition number 1. So in the first example I used, sodium was there high up there, but hydrogen was so much down here. They are so far apart. So condition number 2 will not work. Condition number 1 has to stand, because condition number 2 says even though sodium is more in the electrolyte, that it will only discharge sodium first if condition number 1 is not totally breached. That is, only if the position of sodium and hydrogen, they are close. So if after sodium you have calcium and then magnesium, if hydrogen was at magnesium's point or calcium, okay, and the concentration of sodium is more than that of hydrogen, the electrode won't say, okay, I'm supposed to discharge the one lower in the series, that's the cathode, the one lower in the series. It will say, okay, since they are so close together, though the other one is lower than the other, which I should discharge first the one that is lower, I will discharge this one that is higher, just one step higher, since they are close, because the one that is higher here, the sodium, the concentration of their ions is so plenty, so much. So that's a little explanation of condition number 2, that the increasing the concentration of that ion can help and influence how it's preferentially discharged only when their position in the electrochemical series are closely positioned. So the effects of concentration becomes less important if the position of the competing ions become further apart, if the position is so wide, so big, the effect of concentration becomes meaningless. So it doesn't take step number 2 if number 1 position, the condition number 1, the position is far apart, then step 2, condition 2 does not work. You understand? Good. Okay, you see an example there. Consider the electrolysis of a concentrated solution of sodium chloride. Now in this solution there are 4 types of ions. You see the cations and the anions, both from the electrolyte and the solvent, which is water. So the electrolyte is sodium chloride, the solvent is water. Sodium chloride is NaCl, the solvent water is H2O. Now both of them have ions, so we separate the cations from the anions of both electrolytes and solvents. The cations in the electrolyte, cation is a positive ion, so sodium, which is the positive. The cation in the solvent is hydrogen. Now the anions in the electrolyte is chlorine, and the cation in the solvent is, or the anion in the solvent is hydroxide. Now we check their concentration. In that example, the concentration of the sodium and chlorine is higher than that of water. You understand? So concentration of sodium chloride is higher than that of water in this question. So take note that sodium is higher in the series than H+, like we used there, and chlorine is slightly lower, a little lower in the series than OH. If you look at chlorine is position number 1, 2, 3, 4, fourth position, and after 2 positions you have hydroxide, so it's not so far apart, it's just slightly further apart. So at the cathode, H+ are preferentially discharged, although the concentration of the Na is far greater, but the great distance between the 2 positions, as condition 1, cannot be bridged because they are too far apart. So the distance between the 2 positions of sodium and hydrogen in the series make the effect of concentration less important. Understand that. But at the anode, chlorine are preferentially discharged. Now, the effect of concentration is important here because the positions of Cl and OH are close to one another in the series. So you see, in this example, condition number 2 has been used and 1 has been neglected because condition number 2 meets the requirements. The positions of the 2 competing ions are close. So condition number 2 can kick off to... so if I want to summarize this, I will say, first of all, the position of the ions in the series will decide which one is preferentially discharged. But if they are close together, the positions are close, then you have to use concentration to decide. So concentration now comes in. That's what we've seen in this example. Those are 2 conditions. Now the last condition, number 3. Remember, the first condition is the position of the ions in the electrochemical series. Second condition is concentration of ions in the electrolytes. We've explained those 2. Now the third and the last condition is the nature of the electrode. Nature of the electrode. Now electrodes which take no part in the electrolytic reaction are described as inert electrodes. There are the electrode, they are made of materials. So these materials can decide if the materials are materials that like hydrogen. You understand? They like to see hydrogen. They like to attract hydrogen, and hydrogen is in that solution. You know, that material will want to bring hydrogen first. I like hydrogen. Like you, if you are someone that likes to eat chicken, and then you go somewhere and you're given assorted types of meats, you're given cow meat, given goat meat, and you know you love chicken so much, and you see chicken, and you know if you start eating others, you'll be tired before you eat chicken. So you have to choose which one would you choose. You're someone that likes chicken, so you will go for chicken. So electrodes, what the material electrode is made of, can help decide which of the ions I discharge first. But now there are some electrodes that do not like any of the ions at all. They are made of materials that don't take part in the electrolysis process. I mean, it only conducts electricity, that's what it does, but it does not favor any ion. It doesn't like any ion at all. So these kind of electrodes are called inert electrodes. Does not react. Inert electrodes. Now, platinum is a material, and carbon, that's graphite in particular, those two behave as inert electrodes. So if you are using platinum electrode, then you're not going to be having problems with the nature of electrodes affecting the electrolysis, because they don't even care which one is first or second. They don't like any of them, so they'll have to deal with condition 1 and 2. But there are some other electrodes that they have strong affinity for certain ions. Like you are the person that have strong affinity for chicken, so you want to be attracting chicken first. Whenever you see chicken, is that one you want. Some electrodes behave like that, and this may influence the ionic discharge. Can influence which ion is discharged first. So let's see example. In the electrolysis of aqueous sodium chloride is sodium chloride dissolved in water. Remember, aqueous solutions are solutions where water is the solvent. So sodium chloride dissolved in water using platinum electrode. Remember, platinum is inert, it will not react, it doesn't care which one I should discharge first, because it doesn't like any of them, so to say. So it will deal with condition 1 and 2. So using platinum electrodes, H plus are preferentially discharged. You know why H plus are preferentially discharged? Because Na, sodium, is far apart, so it's using condition number 1. And if a mercury cathode is used, mercury now has a strong affinity for sodium. So if mercury cathode is used, the mercury will tend to associate with the sodium to form sodium amalgam. So it will the discharge of sodium requires less energy. It will, since mercury has strong affinity, it likes sodium, it will first of all catch sodium to itself, dissociate that sodium. So hydrogen has to come later. You see how the material used in making the electrode can affect. So that's where condition number 3 comes in. If you are not using an inert electrode, then the material the electrode is made of can affect the preferential discharge, depending on which ion does that material prefer, which one does it like most. Good. Now, other electrodes may also influence the ionic discharge because they possess characteristics similar to those of the ion in the electrolyte. Example, if a copper anode, yes, the anode is made of copper, is used in the electrolysis of a solution of copper 2 tetrahydrosulfate 6. Copper anode is already copper, made of copper, and then the electrolyte has copper in it. What do you think will happen? Now, neither the tetraoxosulfate 6 nor the hydroxide in the water will be discharged. They will have to wait. Instead, the copper atoms from the anode, the copper in material, the electrode which is made of copper, the atoms in that copper will go into solution. They will dissolve into the water, and will give up their electrons more readily. So you understand what will happen. The copper will first of all like to discharge copper and leave tetraoxosulfate 6 ions and the hydroxide in the water. So this principle is used in the extraction and purification of some metals. So good. So that is ionic theory and preferential discharge of ions. Okay, so now that's how electrolysis happens practically. Now, how do we calculate what has happened during electrolysis. So we move to the next step. Faraday's laws of electricity. We all know Michael Faraday, right? Good. Now, he made two laws concerning electrolysis. So we're going to look at these two laws one by one. Faraday's first law of electrolysis. Now, Faraday's first law of electrolysis states that the mass, M, of an element discharged during an electrolysis is directly proportional to the quantity of electricity, Q, passing through it. So, if you want to put that in formula way or represent what you just said in mathematically, you say, since they said the mass of an element, so M, during an electrolysis is directly proportional to the quantity of electricity, so the sign of proportionality to the quantity of electricity. So M is proportional to Q. Now the unit of quantity of electricity is coulomb. So unit for Q is coulomb. So when you be saying the quantity of electricity, you say maybe it's 500, so 500 coulombs. You understand? So units for measuring electricity is coulomb, and the symbol is Q. Now, okay, symbol for coulomb is C, but the symbol for quantity of electricity is Q. So when you say quantity of electricity, you can write that as Q. And how many is it? Equal to 500 coulombs or whatever it is, but you may not spell out coulomb. 500 C, capital C, or you spell out 500 coulombs, as the case may be. Now, this unit of quantity of electricity, which is measured in coulomb, is not measured directly. It is derived from the measured rate of the flow of electricity. As you know, flow of electricity is the current times or multiplied by the time it takes. So since we say that Q is not measured directly, Q is a measure of the current times time, then we can say that Q is equal to current times time, and we put that mathematically. Q equals to I times T. I stands for current, T stands for time, and Q stands for quantity of electricity. So the quantity of electricity is equal to the current passing through the electrolyte multiplied by the time it takes. Alright, so that's the formula for the first law of electrolysis. Q equals IT. Now, the first law of electrolysis can also be stated as follows. The mass of an element discharged during electrolysis is directly proportional to, number one, the magnitude of the current. Since we say Q equals IT, the I part now, the magnitude of the current. And number two, the time of flow of the current. The T part of the Q equals IT. So, the quantity of the mass of element discharged during electrolysis is proportional to the magnitude of the current, how much current, and how much time it takes for the current to flow. So if we bring that down mathematically, it's okay. Mass, the mass of elements, the mass of element discharge M is proportional to the I current and T time multiplication. So we can also, if you want to change the sign of proportionality to sign of equality, you have to introduce a constant. So to change that, M is proportional to I times T to a sign of equality. We say M equals to, we introduce a constant. The constant is Z. So M equals Z I T. Now Z is a constant which is equal to the value of 3.3 times 10 raised to power minus 14. So we can use this to calculate for the mass of element discharged during electrolysis. Okay, so take note. When mass is expressed in grams, the constant Z is the mass in grams of the substance liberated by the passage of 1 coulomb of electricity. That is, the a current of 1 ampere pass for 1 second is 1 coulomb. So, and it's known as the electrochemical equivalent of the substance. But I've summarized that and given you the figure. It should be 3.3 times 10 raised to the power minus 14. Okay, so that's Faraday's first law of electrolysis. Now, Faraday's second law of electrolysis. The minimum quantity of electricity required to liberate 1 mole of a singly charged ion, such as hydrogen or chloride ions, is 96,500 coulombs. That's not the law yet. The smallest amount of electricity you need to liberate only 1 mole of a singly charged ion is 96,500 coulombs. That's the amount of electricity you need. Now, this quantity of electricity is called the Faraday. Since it's by Faraday, we give him that respect. Called the quantity of that's 96,500 coulombs is called 1 Faraday. So, and it's denoted by letter F, Faraday F. So the discharge of 1 mole of the singly charged ion M plus is just 1 electron that will be dissociated, so that will be added, so it's 1 Faraday you'll be using. Now look at the equation. M plus M positive plus E minus was deposited as M. Remember we said since M has only 1 positive ion, it's going to need to lose that 1 positive ion to become neutral, right? Good. So how many electrons does it need? It needs just 1 electron, right? Good. So that 1 electron, if it gains that 1 electron, it becomes since it was positive, it has to gain electron which is negative to become neutral. Since it had 1, it gains 1 electron and becomes neutral, deposited as neutral M. Now for the other one that has negative, if A has 1 negative electron, then it has to lose that 1 electron. Now when you lose the electron, you become more positive. So it has to lose that 1 electron and become neutral as A. So because it is gaining 1 and the other one losing 1, but it's only 1, right? Good. Then you say you need only 1 Faraday. You need the minimum quantity of electricity required to liberate that 1 mole. See, remember, since it's just 1 electron, it's gaining or losing on the other way, then you are liberating just 1 mole because a singly charged ion. So since you are liberating 1 mole, you need only 96,500 coulombs of electricity. So you just need 1 Faraday of electricity. Good. Now you remember that we said in Avogadro's law that 1 mole of any substance contains 6.02 times 10 raised to the power 23 particles, in this case electrons. That means that if we need 96,500 coulombs to liberate 1 mole of this ion, it means indirectly we are saying that we need 96,500 coulombs to liberate 6.02 times 10 raised to the power 23 particles of that element, right? Because 1 mole is the same thing as saying 6.02 times 10 raised to the power 23. Now if we say this, then it means that 1 Faraday is equal to 1 mole of electron. So 1 Faraday is equal to 6.02 times 10 raised to the power 23, since 1 Faraday is used to deposit just 1 mole of ion. You understand that? So if 1 Faraday discharges 1 mole of ions of a univalent element, same one, such as hydrogen, sodium, silver, and chlorine, it means that if 2 Faradays will be needed to discharge 1 mole of a divalent element. So now 2. So divalent, 2, di, 2. So since you needed 1 for the other one that was 1, you need 2 for a divalent element or a radical, such as zinc or tetraoxosulfate 6. So look at the equation. The first one we said M positive plus electron. Since there was just 1 positive charge, and there just 1 electron. But this other one now, since M has 2 positive charges, it will need how many electrons? 2. So 2 electrons to be deposited as neutral M. And so A also had 2 negative electrons, negative charges. So it's going to need to lose 2 electrons. So it loses and becomes deposited as neutral A. And that's in accordance with Faraday's second law of electrolysis, which states that, listen to Faraday's second law of electrolysis, when the same quantity of electricity is passed through different electrolytes, the relative number of moles of the elements discharged are inversely proportional to the charges on the ions of the elements. So it's proportional to the charge the element has. Like M had 2 plus. Okay, so we'll need 2 Faradays. A had 2 minus. Okay, so we need 2 Faradays. You understand? So when the same quantity of electricity is passed through different electrolytes, the number of moles of the element discharged will be inversely proportional to the charges on the ions of the elements. Now, we're going to see some examples. Number 1. Determine how many moles of electrons are transferred when 4,825 coulombs of electricity are passed through an electrolytic cell. And the question has reminded you that 1 Faraday is equal to 96,500 coulombs. So from this question, we are asked to find how many moles of electrons that 4,825 coulombs of electricity will liberate. How many moles? Now, we know that 1 Faraday would liberate 1 mole, right? So if 1 Faraday is 96,500. So if 96,500 coulombs can liberate 1 mole of electron, then we are asked how many moles will 4,825 coulombs liberate. So 4,825 coulombs will simply liberate 4,825 divided by what can liberate 1 mole, which is 96,500. And if we divide that, we'll have 0.005 moles. So it therefore means if 96,500 coulombs can liberate 1 mole of electrons, then 4,825 coulombs, which is very much smaller than 96,500 coulombs, will be able to only liberate 0.005 moles of electrons. So you see, since the current is now small, it's not able to liberate up to 1 mole. But since the other one was bigger, 96,500, which is enough to liberate 1 mole, then 1 mole was liberated. So that's the first calculation. That one is the simplest actually. So let's get to more complex ones. Question 2. What number of moles of copper 2 plus will be deposited by 360 coulombs of electricity? Is still like the first one, but this time copper is 2. Copper 2 plus. Now we have to first of all use Faraday's second law to break down and see how many Faradays are used, how many electrons are liberated. You understand how many electrons are lost or gained, so that we can decide how many Faradays are used. So you see, you write out the equation. It said that Cu2 plus had to gain 2 electrons because it has 2 positive charges there. So it has to gain 2 electrons to become deposited as neutral copper. So since it gained 2 electrons, it means we are going to use 2 Faradays. And 2 Faradays is 96,500 times 2. So 2 Faradays needed. Now, since we know 2 Faraday is 96,500 times 2, which equals 193,000 coulombs of electricity for 2 Faradays, then we say if that quantity, that's 193,000 coulombs, liberates 1 mole of copper, since in that equation you see that copper was just 1 mole. You know if it's mole since you're not seeing any number in front of the back of copper. You're not seeing anything, so it means copper is just 1. If it was more than 1, you would see 2. Good. So it liberated just that 1 mole. Since it was 193,000 columns of electricity liberated 1 mole of copper, then how many with 360 columns liberates? Just the same way we did the other one. It will liberate 360 times 1 mole all over what how many columns liberated that 1 mole, also all over 193,000 columns. So if we calculate that, we see that we have approximately 1.87 times 10 raised to power minus 3, which that's in standard form, so it's 0.001865 moles that 360 columns would liberate. So that's so simple to calculate. If you follow the way it's done there, you will see that it's quite simple to understand. Now, if you follow the same pattern, you can solve question 3. But let's look at question 4. Question 4 says, during the electrolysis of copper 2 tetraoxosulfate 6 solution, a steady current of 4.0 times 10 raised to power 2 ampere flowing for 1 hour liberated 0.48 grams of copper. Now we are asked to calculate the mass of copper liberated by 1 column of charge. So we have been given that charge is just 1 column of charge, and that we are asked to calculate mass. Remember that formula, Faraday's first law of electrolysis, that M equals to ZIT. So we can use that formula to calculate for the mass. So if M equals ZIT, and we are asked to calculate the mass of copper liberated by just 1 column. So we are indirectly asked to find that constant Z, since it's constant is a unit. Otherwise, you see in the equation, mass is already given. So you cannot be asked to find mass, and mass is already given. So that's why it's good to write out your given first. If you write out your given, then you know what you need. Your mass is given in the equation, current is given, and time is given, but Z is not given. It should be given. So that's what we are asked to find. So if you use the formula M equals ZIT, you can substitute Z. So Z will become M all over IT. If you substitute your figures into that, your mass was 0.48 grams, and then your current was 4 times 10 raised to power 2, and your time is 1 hour. How many seconds are there in 1 hour? 60 minutes make 1 hour, 60 seconds make 1 minute. So to find how many seconds in 1 hour, you have to do 60 seconds times 60 minutes, which gives you 3,600 seconds. So that's the time you are going to use, not in minutes right now. So 3,600 seconds. If you calculate that, you see your answer comes out 3.3 times 10 raised to power minus 10, which is close to our constant there, Z, which is 3.3 times 10 raised to power minus 14. Alright, now that's not the same as question 3, 2, and 1. But study question 1, 2, 3. Everything in this book, you have to study them very, very well. But we'll see one more time. We'll see question 5. Question 5 says, calculate the mass of silver deposited when a current of 2.6 ampere is passed through a solution of a silver salt for 70 minutes. And you'll be given that the mass of Ag, molar mass of Ag is 108. Ag is silver. And 1 Faraday, you have been reminded once more that 1 Faraday is 96,500 coulombs. So we are asked now to find the mass of silver deposited. Mass of silver deposited. We're going to do this one in a different way, not with the formula M equals ZIT now. Now, we're going to start by calculating the quantity of charge. You remember Q equals IT, that's the quantity of charge equals current times time. That's what we're going to use first to find what's the quantity of electricity even used in this problem. So if we use Q equals IT, and we know that our current in the equation is 2.6 ampere, so we put our 2.6 for I, times, we've been given 60 minutes as time, and 60 minutes is made up of 70 minutes. 70 minutes is made up of 70 minutes times 60 seconds. So we have that in seconds. So if you multiply that second, the figure in seconds by 2.6, you have 10,920 columns. So it therefore means that in this problem, the quantity of electricity that was used was 10,920. Now we can now use that to find the mass. And if we use the first method to say, okay, since silver was deposited, let's see how many electrons, how many Faraday was used. Now, in the equation, it was just silver. Mass, calculate the mass of silver deposited when that current was passed through a solution of a silver salt. So, and we're told that Ag is 108. So, since Ag is 108, the molar mass of Ag is 108. It means it just liberated one molar mass, one mass of it. So it means it's one mole. It's not 2. It's not 3. 1 mole of it. So, but that mole, you're not going to use mole this time because we've been given the mass, molar mass. We're going to use molar mass. So Ag had only one positive charge. So we are going to need one negative charge. So one electron was used to become deposited as neutral silver Ag. So since one electron was used, 1 Faraday was used to liberate 1 mole of Ag, which is 108 grams. So we're going to use 108 grams instead of 1 mole now because we have been given the grammage. So 1 Faraday is used to deposit 108 grams of silver. And 1 Faraday is 96,500. So since 96,500 column liberates 108 grams of Ag, then the quantity of electricity we calculated, 10,920. How many mass of silver will that quantity liberate if 96,500 liberated 108? So simply, just like we did the other one, 10,920 columns will liberate 10,920 times. Remember the other time we used 1 mole, since it was just 1 mole that was not given gram. But instead of 1 mole now we're going to use the gram, 108 grams. So 10,920 times 108 divided by what liberated the whole 108, 96,500. Good. And if you calculate that, you see that you have 12.22 grams. So 10,920 columns was able to deposit 12.22 grams of silver, whereas 96,500 columns liberated 108. So I did this so you can see that you won't have to use 1 mole like the other one. When you are given the grammage, molar mass of that element that's liberated, you use that instead of 1 mole. But if you're not given and you know it's just 1 mole, just write 1 mole and use 1 mole. Okay. Now, question 6 is somewhat complicated, but I need you to go down with me. Calculate the volume of oxygen evolved at 285 Kelvin and 0.91 times 10 raised to power 5 Newton meter square when a current of 2.5 ampere is passed through acidified water for 1.5 minutes. Now you've been given all what you need. Molar volume of gas at STP is 22.4 dm cube, you know that. Standard pressure is 1.01 times 10 raised to power 5. You know this is the standard pressure. You can say it's 1 atmosphere, or in Newton meter, since the question is dealing with pressure in Newton per meter, then 1 atmosphere is the equivalence of 1 atmosphere in Newton meter is 1.01 times 10 raised to power 5 Newton meter. So that's standard pressure. And 1 Faraday, again, you're reminded that is 96,500 columns. So first of all, we start by finding the quantity of electricity since we are not given in the equation. So we find it using Q equals IT, and the current I was 2.5, and the time being 1.5 minutes is made up of 60 times 1.5 seconds. So we break down to seconds, and we see if we calculate that our quantity of charge is 225 coulombs. Now we take our second step to see how many Faradays was used. Now we write out the equation. 4OH minus, now you don't add 4 first. 4 was added when you're balancing the equation. So OH minus yields H2O plus O2. Now we're given that O2 in the liquid form is 22.4 dm cube. Remember, molar volume of any molar volume of a gas is 22.4 dm cube. So transfer that to that is a gas. It's 22.4. So since if we balance that equation, we discover that OH on the left hand side of the equation has to be 4 moles. So since it's 4 moles, 4 Faradays will be needed. So you see that the 4 affects the charge there because it's mole now. Mole number will affect the charge. So OH had only 1 minus. 4 moles of OH will have 4 minuses. You understand? So 4 anions, 4 negative charges. So since it's 4 negative charges on the other end of your equation, you will need 4 electrons. You will need to lose 4 electrons. So if you're losing 4 electrons, you see 4 Faradays are used up. So, and you know, to calculate 4 Faradays, 4 times 1 Faraday, which is 96,500. So 4 times 96,500 coulombs will give you the quantity of the amount of electricity that's liberated for that's 4 electrons. Now if you do that, and in our usual manner, if 4 times 96,500 coulombs liberated that's gas, that 22.4 dm cube of gas, then how many volume of that gas will 225 coulombs, which is in the equation we are asked, we calculated that quantity Q equals IT, we had 225 coulombs. How many volumes of O2 gas will that 225 coulombs liberate? Then in our usual way, it will liberate 225 times, since this is a gas now, it's 22.4 instead of, to say 1 mole, or we say the mass. Since it's not a solid, to say we have a molar mass. Since the gas, the volume is 22.4. Since it's 1 mole, it's just 22.4. So it will be 225 times 22.4 all over what liberated 4 electrons, which is 4 Faradays, which is 4 times 96,500. If you put that in equation, you will discover that 225 coulombs was able to liberate 13.06 cm cube at STP. Now you've gotten your charge needed. Now the equation is asking calculate the volume. You're not asked to calculate the charge, how many it was able to liberate or whatever. You're asked to calculate volume of oxygen evolved. So after finding this, we have to use gas law, general gas law, to find the volume. So we now have all the parameters needed. So we have to convert the volume at STP, as we have to convert 13.06 cm cube, which is at STP, to its volume at what is asked in the question. We are asked to find the volume at 285 Kelvin, and that's 0.91 times 10 raised to the power 5 Newton meter pressure. So we have to convert 13.06 to the volume at 285 Kelvin and 0.91 times 10 raised to the power 5 Newton meter. So we use a general gas equation to do that conversion. So general gas equation is P1 V1 all over T1 equals P2 V2 all over T2. So we have our P1 being a standard pressure. Standard pressure is given in the equation as 1.01 times 10 raised to the power 5 Newton meter, and V1 is what we just calculated, finished calculating, which is 13.06 cm cube. T1 is since P1 was standard pressure, T1 has to be standard temperature, which is 273 Kelvin. T2 then will be what the question gave us, 285 Kelvin. And P2 will become what we were given in the question, 0.91 times 10 raised to power 5 Newton meter. Take note, if P1 is standard pressure, automatically T1 will be standard temperature. And we're asked to find the other volume, V2. V1 is what we've gotten, 13.06. Don't say V1 is going to be 22.4, because we use that 22.4 to calculate that 13, to calculate and find that 13.06. So it's embedded in it. So V1 is 13.06. V2 is what we are to find. So if we make V2 subject formula in the equation, V2 becomes P1 V1 T1 all over P2 T1, which if you substitute your figures in accurately, you will see that V2 equals to 15.13 cm cube. So the volume of O2 liberated at STP was 13.06 cm cube, but at the conditions we are given in the equation, the condition of 285 Kelvin and 0.91 times 10 raised to power 5 Newton meter pressure, the volume is 15.13 cm cube. So the volume of oxygen evolved at 0.91 times 10 raised to power 5 and 285 Kelvin is 15.13 cm cube. Now, if that's the way we calculated that thing looks complicating to you, you can listen to this audio again and again and again until you understand very well. Now let's see some examples of electrolysis. When we're saying electrolysis, let's see some substances that were passed through electrolysis process, and let's see the results. Number one, electrolysis of brine. When we say brine, we just mean aqueous sodium chloride, NaCl. Sodium chloride dissolved in water is called brine. It's just called brine. So electrolysis of brine is electrolysis of aqueous sodium chloride solution. Okay, three important chemicals: NaOH, sodium hydroxide, Cl2, chloride gas, and H2, hydrogen gas, can be obtained by electrolyzing brine, that's aqueous NaCl solution. The electrolysis of brine yields hydrogen and chlorine at the electrodes and a concentrated solution of sodium hydroxide. And you will see how that is done. The electrolytic cell in the industrial electrolysis of brine is known as the Kellner-Solvry cell. The Kellner-Solvry cell. Now the anode is made of graphite, carbon. The anode is made of carbon material, graphite in particular. You know, carbon has two allotropes, diamond and graphite. So graphite is still an allotrope of carbon. So it's made of graphite, which is a carbon allotrope, dipped into brine, dipped into the aqueous sodium chloride solution contained in a tank. So there is a tank, and the anode and cathode, the anode, which is made of graphite, is dipped into that tank, and the tank contains the aqueous sodium chloride. Now, fresh sodium chloride enters at one end of the tank. Fresh sodium chloride is entering at one end of the tank, while the one that is used, the used sodium chloride, this is brine, overflows from the other end. So a layer of mercury flowing in at the base, mercury at the base of the tank in the same direction as the brine, acts as the electrode, as the cathode. Remember, the anode is made of graphite, which is carbon. Now the cathode is made of mercury. That's what it means. Now, since brine is less dense than mercury, is not as heavy as mercury, it floats on top of the mercury layer. Since it's lighter than mercury, it will float on top of mercury. Now, let's see what happened at the cathode and at the anode. Now, at the anode, chlorine is produced. Remember, the anode is made of graphites. Good. And the anode is the positive electrode. So, chlorine is a negative ion. So, it will move to that positive electrode. So, when the chlorine in sodium chloride, that's brine, NaCl, the chlorine part moved, which since it's negative, moved to the positive electrode, which is the anode, and then deposited the negativity in it, in the electrode, since anode is looking for electrons, doesn't have, so it goes there and loses its electrons, and then it becomes free chlorine atom. It has lost its electron. So when it lost electron and it becomes free, we have gotten out our chlorine. Is that free chlorine? It's free now. You can get it as it's a gas now. So chlorine is produced at the anode. You see the equation there. Now, but at the cathode, the sodium ions, you see chlorine has been deposited. It was sodium chloride. Chlorine has faced its own wahala. Now, so the sodium ions which are attracted to the cathode, the cathode is a negative electrode. Sodium is positive ion, so sodium positive will go to the cathode negative, and then it will gain electrons. Now, remember when we said that mercury, if your electrode is made of mercury, mercury would like to ionize sodium first. Now, this is sodium. So, when this sodium goes and meets the cathode, and discovers this cathode is made of mercury, wow, it will form association with the mercury, since mercury likes sodium. Now, when it forms that association, it will produce what is called sodium amalgam. When it produces sodium amalgam, the amalgam is drained from the cell at one end and led to a second tank that one can be processed later, while fresh mercury is continuously supplied to the cell from the other end. Now, in this other second tank where we have carried out the sodium amalgam into, the amalgam is treated with water, where it decomposes to produce sodium hydroxide. Remember, the sodium is there and we put it inside water. Water has hydrogen and oxygen in it. Okay, the sodium will cling to the hydrogen and oxygen, OH, and form sodium hydroxide. Now, when it forms that, hydrogen also will be formed, and since mercury was part of it, it formed association with it, mercury also will be liberated. So it means at the cathode, three things are formed. We have sodium hydroxide, we have hydrogen, and then mercury. Read it well, you understand. You see the equation there. At 2Na, which formed sodium, which formed an amalgam with mercury. Mercury is Hg, plus when it was added to water, H2O, then Na changed neighbor, went to oxygen and hydrogen, formed sodium hydroxide, and then you see that out of 2H2O, Na has carried one H and one O, so how many H will be left? 2H. It was 4H and one oxygen. It has carried the only one oxygen and one hydrogen, so 3 hydrogens left. Okay, the two hydrogen leaves and becomes hydrogen gas, and the other one hydrogen is liberated, and then we have mercury coming out too, since they have it has lost the association which sodium had with the mercury, which is sodium amalgam. So in the electrolysis of brine, take note, in the electrolysis of brine, you can underline that the product, first of all, the anode is made of graphite, which is carbon, and the cathode is made of mercury. And the product at the anode, the chlorine is produced, so we get our chlorine out through the anode, and then at the cathode we get 3 useful substances, which are sodium hydroxide, we get hydrogen, and then mercury. So that's why at the beginning of electrolysis of brine we said three important chemicals: sodium hydroxide, chlorine, and hydrogen can be obtained by electrolyzing aqueous sodium chloride. So sodium hydroxide and hydrogen was gotten at the cathode, then chlorine was gotten at the anode to make up the three important chemicals. So we look at another example: electrolysis of copper. Now I need you to listen very attentively. Electrolysis of copper can happen with different materials of electrodes. So we're going to see different materials now. Now, electrolysis of copper 2 tetrahydrosulfate 6 solution using different anodes. Now, the electrolysis of aqueous copper 2 tetrahydrosulfate 6 using carbon or platinum electrode yields deposits of copper at the cathode and oxygen at the anode. So now we want to see platinum electrodes being used. Now, you see the breakdown of the cation, the anions, and the concentration and the position in the series, so that we know which one be discharged first. The cation Cu 2 plus in CuSO4 and H plus in H2O. The anions SO4 2 minus in CuSO4 and OH minus in H2O. The concentration of ions of CuSO4 is higher than that of water, but the position in electrochemical series, Cu2 plus is just slightly below H plus in the series, while OH minus is higher in the series than SO4 2 minus. That's going to be helpful in deciding which one is discharged first. Now, at the cathode, both Cu2 plus and H plus, that's both the cations in the electrolyte and the solvents, migrate to the cathode. Since they are positive ions, they migrate to the negative electrode, which is the cathode, where Cu2 plus is discharged preferentially. Cu2 plus is discharged preferentially because Cu2 plus is below H plus. The Cu2 plus acquire 2 electrons. Since it had two positive charges, so it will need 2 electrons each from the cathode to be deposited as metallic copper. So it becomes free, normal atom metal, free metal now, copper, on the cathode. As a result, the cathode gradually grows thicker. It's collecting ions. Now, this reaction is the same whether it's a platinum or carbon or copper cathode is used. So you always have at the cathode, whether you're using platinum material for your cathode, or you're using carbon material as your cathode, or you're using copper material as your cathode, Cu2 plus is always going to be discharged preferentially. So at the cathode, using three types of materials now, Cu2 plus is always discharged. But at the anode, the type of material used can affect. Now, at the anode, if you are using carbon or platinum, both SO4 2 minus and OH minus, so the negative ions, will move to the anode, which is the positive electrode. Now, OH minus will be preferentially discharged as oxygen gas. Why? Because in the anion side, the anion with the higher position in the series is discharged first, while in the cation side, the cation with the lower position in the series is discharged first. So now this is anion side. So, and OH minus is higher in the series than SO4 2 minus. So OH minus is preferentially discharged and discharged as oxygen gas. Take note. Now, the positions of the ions in this series are important in this and the anode. Now, if you look at the equation, you see OH minus produces OH plus electron. It lost that one electron. So when that happens, you see OH had to combine with another OH to form water molecule and oxygen. So that's how that oxygen is now out free. So you see H2O plus O, so O is out. So that's why it's discharged as oxygen gas, because it's from water and oxygen. Oxygen is free. Now oxygen gas is diatomic. Remember, it cannot exist as just O. It has to bond with another oxygen in the atmosphere to become O2. That's what you see in that your equation. So as a summary, the cathodic half reaction, Cu copper is produced from at the cathode, and at the anode oxygen is liberated at the anode. But the anode, if you are using carbon or platinum material for the electrode, but at the cathode, matter if you are using platinum or carbon or copper, it's going to still produce Cu. Good. Now remember, since Cu was discharged, H plus was still waiting. So Cu left and H plus was still waiting. And you know, when you hear H plus, you were thinking of acid. So H plus is still waiting. Now an OH here has been removed, and when you hear OH, you think of basic properties. So OH is removed, but the acid is still there, the H plus is still there. So it means that solution is becoming more acidic because H is still present, but OH, which should have even neutralized that acid, has been taken away. And so when the Cu2 plus at the cathode and the OH at the anode has been discharged, the solution becomes acidic. You understand that? Due to the H plus and SO4 2 minus which remain in the solution. So H plus SO4 2 minus is what we call tetrahydrosulfate 6 acid. So remember, we are dealing with electrolysis of copper 2 tetrahydrosulfate 6 solution. So remember, H plus is still present there, which makes that whole solution acidic. So in the electrolysis of copper 2 tetrahydrosulfate 6 solution, after the electrodes, the cathode has displaced the copper and the anode has displaced the hydrogen, the solution becomes more acidic. Now remember, we said in the cathode you can use any of these three, platinum, carbon and copper. It will still produce copper at the cathode. But we've seen how carbon or platinum at the anode can liberate hydroxide as oxygen gas. Now let's look at if the anode was made of copper. If a copper rod is used as the anode, in as much as the OH and SO4 minus ions migrate there, remember, none of them is discharged. Rather, the metallic copper atoms on the surface of the electrode go into solution by losing 2 electrons each to form Cu2+. So you remember now, copper electrode is used and copper is in the solution. So copper will be liberated, Cu2+, then migrate to the cathode to pick up the 2 electrons that were lost at the anode and get deposited as copper metal. So even at the anode, if the anode is made of copper, yes, you will see that copper will be also discharged at the anode, while copper was also discharged at the cathode there. So you see that OH minus and SO4 2 minus will remain there. But when you are using the anode of carbon and platinum, H plus and SO4 2 minus remained. Now you are using copper. Now remember, the cathode there is waiting. It wants to discharge. It wants to liberate copper. So it's waiting for any trace of copper. And since you were using copper anode now, the copper anode now dissolves itself. The electrode itself dissolves into the electrolyte. And when it dissolves, it's running to the cathode. Since cathode is discharging copper, so it goes to the cathode and it's discharged too. So you will discover that the anode will keep transferring itself to the cathode, and the anode will keep reducing because it's dissolving itself into the solution and it's transferring to the cathode. Since the anode is transferring and is getting reduced, the cathode will become fatter, increasing. So the original ions from the salt and water still remain in solution. So that's why, since the original ion and the salt, they are still there, the color, the concentration, and the pH of the electrolyte remain unchanged, because H plus is still there, OH minus is still there. So the concentration is the same, the color has not been changed, and every other thing remains the same. It's just copper doing its business. Copper at the cathode, copper at the anode, just transfer of copper from anode to cathode, and a reduction in size of the cathode or the anode, and increase in size of the cathode. So in summary, CuSO4 contains Cu2 plus, SO4 2 minus, H plus, H3O plus, OH minus ions. Now number 1, Cu2 plus and H3O plus migrate to the cathode. Cu2 plus discharged, copper discharged at the cathode and deposited as copper metal. So, and the copper cathode increase in mass because it's deposited there. Now, copper anode, if you're using copper as the anode, dissolves and ionizes. And since it's dissolving the electrode, it decreases in size to give copper 2 ions. And that copper 2 ions will go to cathode, right? And is discharged. So solution remains blue. Concentration of Cu2 plus ions is constant. You know why concentration of 2 plus ion is constant? Because it's just circulating, discharge here and go and reach there. The other one is just, it enters the electrolyte, goes to the cathode. It's also in the anode. So you see the equation there. At the anode, Cu as solid goes into, ionizes itself and goes into the solution and forms Cu2 plus in solution, AQ, CAQ, and it becomes an electrolyte. The anode now becomes an electrolyte, and then it's transferred to the cathode. The cathode keeps increasing, anode keeps reducing. Now, the third one is electrolysis of acidified water. Electrolysis of acidified water. Now, acidified water is just made by adding a few drops of tetraoxosulfate 6 acid to water. So if you add a few drops of tetraoxosulfate 6 acid to water, that's acidified water. Acid in water, acidified water. Now, the electrolysis of acidified water is the same as the electrolysis of dilute tetraoxosulfate 6 acid. Both electrodes used are platinum foils. So both electrodes are made of platinum materials. Platinum is inert. It doesn't concern itself with which one I like most, or which ion I like most. So acidified water contains the following ions: the cations for the electrolyte and the water. Cations in electrolytes H2SO4 is 2H plus, since H is 2 there, and in water is H plus ions, and anions is a SO4 2 minus for the electrolyte, and OH minus in the water. So the concentration of ions of the electrolyte is more than that of the water, so it's higher than that of the water. But the position in electrochemical series, OH minus is higher in series than SO4 2 minus. So the anode will prefer OH minus. So let's look at the cathode. The H plus, which are the only cations present, since you know that the cation in the electrolyte is 2H plus, and that of the water is still H plus, or is still H. So H ions, hydrogen ions, are the only positive, the only cations present. So they all migrate to the cathode, to the negative electrode, where they acquire an electron each to form neutral hydrogen atoms. So hydrogen is liberated there at the cathode. These atoms then combine in pairs to form diatomic molecules as gaseous hydrogen. Hydrogen is diatomic, so since one was discharged, it will have to combine with hydrogen in the air and form diatomic hydrogen, and it's gone. It's liberated as gas. But at the anode now, both SO4 2 minus and OH minus migrates to the anode, but OH minus are preferentially discharged. Now, each OH minus loses electrons to the anode to become a neutral OH group. Now, two OH groups react to form one molecule of water. So if you add OH plus OH, you are going to get H2O plus oxygen. So it will react to form one molecule of water and one atom of oxygen. Since oxygen is diatomic, you see the equation. it will have to combine with oxygen in the air to form diatomic oxygen. You can see that in the equation. So in the summary, at the cathode you see what happens, and the anode you see the equation, the reaction that happens. Now there's one important thing I want you to note in the electrolysis of acidified water. Take note of what I'm going to read now. The electrolysis of acidified water yields 2 volumes of hydrogen. 2 volumes of hydrogen. Take note, since hydrogen was in the electrolyte and also in the water, they both go there and they are both discharged because they are the same elements. So 2 volumes of hydrogen at the cathode and 1 volume of oxygen at the anode. Now, see, in the anode, at the anode, OH was competing with SO4 2- and OH1, so SO4 2- is still in the solution. So OH is discharged as oxygen. So it's only OH, only oxygen that is at the anode. So only one volume of oxygen at the anode. That is, the ratio of hydrogen to oxygen by volume is 2:1. Now you're going to use that in calculations. Take for instance, if 1 dm cube of gas evolved at the cathode during the electrolysis of acidified water, what was the volume of gas evolved at the anode? And you already know that the ratio of the product formed at the cathode and anode in electrolysis of acidified water is 2:1. 2 being that volume of hydrogen and 1 being volume of oxygen. So if the ratio of cathode to anode is 2:1, then 1 dm cube of gas evolved at the cathode will yield 1/2, since this side is 2 and the other one is 1. So 1 dm cube takes the 2 parts, since hydrogen is at the cathode, takes the 2 of the part of the ratio. So the other one will be 1/2. 1/2. 1/2 of 2. So 2:1 means 1 is half of 2, so half. So 1 dm cube of cathode will yield half at the anode. So half of 1 dm cube will be 0.5 dm cube, simply 500 cm cube. So it's important to note that the electrolysis of acidified water yields 2 volumes of hydrogen at the cathode and 1 volume of oxygen at the anode, and that the ratio is 2:1. Hydrogen taking the 2, oxygen takes the 1. Okay, now as the last part of this topic, we'll look at the uses of electrolysis. Now, we remember when we were studying that we said electrolysis is used in extraction of metals. Most metals are purified and extracted using electrolysis. So number 1, extraction of elements. Metals, example, sodium, potassium, magnesium, calcium, aluminum, zinc, and others. And non-metals like hydrogen, fluorine, chlorine are obtained either by electrolysis of their ores or the electrolysis of their fused compounds or their aqueous solutions. All those things we were saying displaces hydrogen at the cathode. So you see, if it displaces hydrogen, then it means we can use that and extract hydrogen. Good. So it displaces chlorine at the other side, the cathode of the other one we did. We can use that to extract chlorine. So that's how it's done. So we can use that to extract this element from their ores. Now, fused compounds, like we said, sodium chloride. Sodium chloride is a fused compound. It contains sodium and chlorine fused together. Or their aqueous solutions as dissolved in water. Number 2, purification of metals. So remember that we said copper. If copper is used at the anode as the material for anode, in the electrolysis of copper 2 tetrahydrosulfate 6 solution, while the cathode is depositing copper, and anode, since it's copper anode material, will also be dissociating copper, then we can use that process for purification of copper. In fact, that's what is used in purification of copper, where the copper that is impure, the impure copper is used as electrode, the anode electrode now. So while it is dissociating into the electrolyte, into the water, it will now drop all the impurity in the water and now run to the cathode which is liberating copper. When it runs to the cathode, it's now pure copper, so it attaches to the cathode. Since the cathode is growing in size, until all the copper from the anode has gone to the cathode, pure copper now. The waste, the impurity has been dropped into the electrolytes as slag. So electrolysis can be used in the purification of metals like copper, gold, silver, or copper, mercury, silver, and gold. Number 3, electroplating or protection of metals from corrosion. Electroplating, so coating a metal that can corrode, that can rust, with another metal that cannot get roasted easily. You can use electrolysis to do that. Number 4, manufacturing of chemicals such as sodium hydroxide and sodium triiosochlorate. Remember, sodium hydroxide was gotten when we electrolyzing brine, since we said sodium will form an amalgam with mercury. So we can, and at the end of the day, when that one is treated with water, sodium hydroxide is produced. So we can use electrolysis of brine. So electrolysis is used to manufacture sodium hydroxide. So manufacturing of chemicals such as sodium hydroxide and sodium triiosochlorate 5 can be gotten using electrolysis. Alright, so that's where we will end for the topic electrolysis. Do well to drop any questions you have on the group and I will answer them. And do your assignments. I'm going to send you assignments, submit it on Sunday, come online on Sunday if Christ tarries, get the notes for next week. And remember to stay safe. God bless you.